So today is a MATLAB day. So it's the first one. We'll have many of these. And what we're going to do is we're going to program here in class. We're going to solve some boundary value problems and relate it back to what we did last time in class. Okay? So we'll switch over to the laptop here in a minute to do some MATLAB programming. It's all in the notes there, by the way, so you can just follow along. A code that works on the notes. There we go. Okay. But we'll go over through the infrastructure of it so you feel comfortable. So as you start getting towards the next homeworks, you'll have sort of an idea of how to do this process. So here's going to be what we're going to solve. Let's go back. It's going to look something like this. Here's the problem we're going to do today. Those are partial derivatives, or just derivatives. Actually, sorry, just derivatives. Okay. Here's what I proposed last time in class. We were looking at something that looked like this, with the boundary conditions that that psi goes to 0, x goes to plus or minus infinity. We're going to make it a little simpler today. Now, notice, today we're doing a different problem. Okay? We are going to actually do this problem. We're going to say, how about we do the following for simplicity? We're going to assume is that the boundary conditions at x equals plus or minus 1 is equal to 0. So I'm going to make the function be 0 at minus 1 and 1. This is not what you will do in your homework. Okay? Understand, this is a toy problem, just to illustrate the concept. That's it. So don't take what we do today too seriously. I mean, take it seriously, but not too seriously. Okay? Okay. So we're going to do a simpler problem. This here, and not only that, there's going to be no n of x. We're just going to make this. I'm going to pick this to be 100. Totally random. But that's fine. We're just going to solve this problem today in class. Okay? So the boundary value problem, because we have on the left and on the right some constraints. Here's your differential equation, and our objective then is to solve this. Okay. So first of all, we need to think about how to formulate this problem, because if you notice what we did in class, we were always solving things that look like this. We built all our time-stepping routines based upon this idea here. So it's important for us to then reframe this in terms of this here. In other words, what we know how to do is step forward systems of first-order equations. And what we have is a second-order equation. There's the two derivatives. So our first job, your first job ever, when you see a differential equation, if you're going to solve it numerically, the first thing you ever do is you turn it into a system of first-order equations. Okay? Make yourself a little flashcard. What do you do first? System first-order equations. Okay? All right, pretend you're in medical school, and that's the only thing you need to know. Okay? That's it. Turn it into a system of first-order equations. Your number one objective, always, for differential equations. Because once you do that, you know how to solve it, because then you can use all the stepping routines. Okay, so let's do it for this problem here. So I have a second-order system. So I got two derivatives there. And so I want to turn it into first. So what I'm going to do is make a transformation. I'm going to define some new variables. Let's call them y1 and y2. Okay? All right, so, and here is what I'm going to do. And this is the standard process for turning any differential equation into a system of first-order equations, is you say my y1, let's make that psi, and my y2 will be the derivative of psi. If I have a second-order system, I only need 2 ODEs. If I have a third-order system, I only need 3 ODEs. It's just like that other one we did, right? Remember the number of constants parameters I have to... Nth order system, I need n coefficients. Nth order ODE, I need n of these. So 2, 2. Good. Everybody good with that? Now here's the trick. Differentiate both sides of both those two equations. They're not even equations. You made this stuff up, right? You're just making up y1 and y2. Remember, Who's got the pen or who's got the pencil? You. You get to do stuff. As long as you don't violate any math rules, like try to divide by 0, it's all you. So you get to make stuff up. I got the pen up in front of the class. I can do whatever I want. And I'm just going to differentiate both sides. Okay? So if I differentiate y1, then I get, let's call it y1 prime is equal to psi of x. So I just differentiated both sides. Now let's just differentiate both sides of this. y2 prime is equal to psi xx. So far just fun and games. Okay? But notice the following. y1 prime is equal to psi of x. But what is psi of x? How did I define it? It's y2. Great. So really, that first equation becomes y1 prime is equal to y2. OK, what about that second equation? y2 prime is equal. Oh, let's put y3 in there. No. There's no y3. Because remember, we stopped at 2. So what is psi xx? By the way, have we used any information yet about our equation? Not yet. But our equation knows what psi xx is. I hope they got that on camera. That was, no, you probably missed it. OK, for at home. There's psi xx right there. Super sweet. Psi xx is, I can move that to the other side. Make it beta minus 100 psi. OK? You have to use this. This is your equation. And it should show up somewhere. And it does. OK? So psi xx is equal to, if I do this, I'm going to get beta minus 100 psi. But by the way, what is psi? Y1. Sweet. So I have just transformed this whole thing to 2 first-order equations. There it is. That is always your first step. You have a differential equation. First thing you ever do, turn it into first-order system. So now this becomes dy dt is equal to f ty, where the y now is y1 and y2. And this is your f, this right-hand side here. Okay, so now we have it back in the framework of what we started off with day 1 of this class. Stepping algorithm. Sorry. Well, this t is the x here. Remember, this is just a representation of abstraction, right? Here, the derivative is an x derivative.